that is also same. ISO is same here, ISO is same here, but exposure here is 1/100th of a second. Here exposure is 1/800th of a second. Low exposure, lesser amount of time the shutter was open, and naturally the amount of intensity is going to be less. So you can increase the exposure by keeping shutter open for longer amount of time. But there are going to be at times not always possible. There will be certain limitations. For example, if your camera is moving fast, okay, then you won't be able to keep shutter open for a long time, because otherwise you will get a blur. And typically in astrophotography, this is what happens when the light conditions are very low. Your camera is all the time moving because it is sitting on Earth, and Earth is moving, Earth is rotating. And then you need different kind of technique. So changing shutter speed is one useful thing. Now here I'm taking example of increasing the amplification. Now here what is happening is, you see the left hand side picture, the exposure is for 1 second and the ISO use is 200. So it is amplification has certain setting of 200. The right hand side picture, the exposure is 1/15th of a second. For a very short amount of time, 15 times lesser amount of time, the camera the shutter was open. Okay, but you amplified it 16 times more because ISO is 3200. So it is 16 times greater than this ISO. So amplification is 16 times greater. The exposure time, therefore, you reduce approximately by same amount. Okay, in the camera 1/16 was not available, so I used 1/15. Okay, what you observe is similar kind of brightness, but not exactly same. What you also observe here on left hand side, okay, there is no graininess. Here there is the graininess, a lot of noise is there. Because what has happened is the electronic sensors have their own noise, okay, electronic noise. So when you amplify, you not only amplify the signal, you also amplify that noise. And that's what creates the grainy picture. So all this becomes relevant when you are also clicking picture in low light conditions. So you can increase the amount of light by increasing aperture. You can increase the amount of light by decreasing the shutter speed, which is increasing the shutter open time. Or you can also increase the amount of light effectively by increasing the amplification of whatever light is received. Okay, everything with pros and cons. Now, we talk about colors. In astrophotography, typically you don't get colored pictures, but all beautiful pictures of Hubble Space Telescope photographs are all colored photographs. So what is done? So let us look at what camera does. So I'll show a photograph which was through camera filter. Okay, these are my students in my lab, and the red filter is on over here. What do you observe over here? And look at the difference between the two. Okay, for example, look at the first girl. You can clearly make out the lipstick here is quite dark. The green filter is on. The red filter is on. The image is very bright, indicating that lipstick must be of red color. Okay, look at the pallu of this third girl. Okay, in the red filter, it is bright, but in the green filter, it is not. It is almost dark over here. Okay, and look at the shirt of this middle girl. Okay, it is relatively less bright over here, and it is more bright in this case. So probably this shirt was of green color. But let us look at the third filter also, the blue filter. Okay, now see what happens in the blue filter. The shirt looks very bright, so probably the shirt is blue in color. Okay, the pallu is dark. Okay, so it was only bright in the red filter, so probably that sari is of red color, and you can clearly make out that the lipstick is dark over here, indicating that lipstick must be red in color. You also see everybody's texture, the human texture is bright in red. It is also bright in green. Okay, but it is relatively dark. Their faces are relatively dark in blue. That's because our body doesn't give out blue light. Body doesn't give out blue light. Okay, mainly it is because of the hemoglobin through the blood, which is flowing in the upper layer of skin. Not upper layer exactly. Okay, below that upper layer of the skin. And that's why when you blush, you become more red because more blood flows over there. Okay, and this is the real picture over here, which you can clearly make out that yes, whatever we were discussing, is over here. It seems there is some chat. There is a question. Okay, it's about. Yeah. Now, just for fun, if you switch off red, okay, and this is possible with the things like Photoshop, okay. If you switch off red, okay, you see that again the lipstick color becomes dark, okay. But you look at the here this pallu, for example, for third girl is quite dark in color, okay. It's more some bluish tinge is there, but it's quite dark. Now, interesting thing is you look at the sari of the first girl. The only green is off. It looks, you see in the real picture, it is blue green. Okay. But when I keep green off, okay, it looks bluish in color. And when I keep blue off, it is greenish in color. Okay. And this is the original, this is the composite image, all images put together. Now, this is how one can study. Of course, Photoshop is an expensive app. My friend, Mr. Shreyas Dongre, kindly did these things and gave it to me. He processed the original photograph and gave the image. Okay, but it is also possible now to do these kind of image processing with Python, which is what one of my students, Mr. Pratik Barve, did. So, okay, these are the same pictures, one in red filter, one in green filter, one in blue filter. No Photoshop used here. The color images was extracted using Python code. Small, just 4-line code he wrote and he extracted this. Now, what you can see here, for example, this is a mint intense, and naturally these leaves must be of green color, the mint leaves. Okay, and therefore you see that they are bright in green, but they are relatively less bright in red. They are even less bright in blue filter. Okay. On the other hand, this extra creamy thing, you see the background here is dark in red filter, background here is dark, relatively dark in green filter, and it is quite bright in the blue filter. So therefore, this background must be blue. And you can look at the orange. The orange is very bright here in red filter. Okay, it is there slightly bright in green filter, but it's quite dark in the blue filter. So we expect that it is orange color, and orange color will be more nicely seen in the red filter and relatively less in the green filter. And you can see the original image is this. So this can be a good nice quiz question for student that, okay, identify which colors are there in different filters, and student we need to analyze things and then come with the answer that, okay, this is what it should be, this is what it should be, and so on. So this is basically color sensation of human eye. Okay, there are cone cells in our eye. They are responsible for color sensation, and there are basically 3 types of sensors. Okay, short wave, medium wave, and long waves. Okay, and they will respond to different spectral regions. Okay, and you see that they are not equidistant. Okay, this is what human evolution has given us. And therefore, typically blue or yellow, our eyes are very sensitive, and the blue light, yellow light, okay, we perceive as brighter things as compared to the blue. So green and yellow we perceive as bright thing as compared to blue. In order to mimic the same thing, what camera sensors do is they have grids, and the sensor is put with filters. So you see here, if you consider a filter of 4 squares, okay, this filter is having red. This particular square has a red filter. This particular diagonally opposite square is a blue filter, and the other 2 squares are green filters. Now, why green is more? Because our eyes perceive more green. The green thing our eyes perceive as more bright, and therefore a very nicely simple design of how a pixel is designed in case of camera sensors, because camera sensor CMOS really doesn't see color. Okay, it will only see, it will only pass current when the light is falling on it. Okay, so it will mainly sense the energy coming from the different photons. Okay, and electronics will convert that energy into the current. But by putting filters, you can get different kind of image, and ultimately you can reconstruct the image. Now, this reconstruction of image becomes very useful when we are looking at photographs which are not only in visible light, but even light which are invisible. Now, filter have other magic also. Okay, for example, one of my students has clicked these 2 photographs. So here this was without filter and the software processing to make it clear. Now, why it is so blurry? This blurry thing is mainly because of ultraviolet glare. Our camera sensors are also sensitive to ultraviolet rays. Many times you may have wondered that your eyes can see sky very nice blue, but when you click that on camera, it may not come that blue. Many times the camera it comes as relatively more whitish in color, and then you are disappointed that I have clicked the good photograph of the sky. Okay, the sky was looking very nice blue to my eye, but in camera it has come more whitish in color. Why is it so? That's because of UV glare. The camera is able to see that ultraviolet, and therefore it and the ultraviolet rays are getting scattered from air, because ultraviolet rays are present in sunlight. Okay, and whatever eyes can't see, the camera can see, and that can put a glare. Now, one way to remove that is you can use the software processing. Another way to do that is you can use a UV filter. Now, of course, this is a different moment because he couldn't click the same moment with UV filter on the camera without UV filter on the camera, but you can see in the same ground in the same time, okay, how clear the picture is, because he has put UV filter on the lens and the clarity improves. Now, these kind of skills, when we understand the physics behind it, okay, we realize that, okay, I mean, should I buy UV filter or not? Now, depends on what kind of pictures I want to click. The polarized filters also have their own advantages. Say, for example, look at this particular picture, left-hand side. This is without polarizing filter. Okay, and what you observe on this floor, there's a lot of light which is coming as a glare. Now, this light we know is the light reflected from the dielectric surface, non-conducting surface is polarized light. And it is polarized in one particular direction. Okay, and when we want to remove that, what we can do is you can use polarized filter. Okay, and you see the glare is reduced. Now, this kind of thing people use, okay, to enhance the effect. Once you understand the optics, once you understand the physics behind it, okay, you know which tools can be used to you can enhance your picture. Now come to imaging in the astronomy. So most objects are faint, objects are at rest, but camera is moving. So because objects are faint from astronomy, except for sun or moon, okay, the stars are going to be faint, and therefore what we will need to do is you will have to keep the shutter open for a long time, but then that becomes difficult because camera is moving along with the earth is rotating. The depth does not matter. So large aperture is a good choice, and that's why people connect their cameras to telescope. Okay, because telescope will have very large aperture. Okay, and large aperture is not a problem. In case of camera, there was a problem. Large aperture means small depth, low depth. But when you are talking about astronomical pictures, okay, everything is effectively coming from infinity. The parallel rays are coming to you. Okay, so you're not really bothered about focusing this or that. And large aperture is a good choice. High amplification is also preferred. So you may increase the amplification, but when you are increasing the amplification, many times the noise may come. The noise from sensor also will be there, because sensor is electronic device, and electronic device will have its own leakage current. You know, ultimately any electronic device is going to have a transistor or those electronic component. They may have leakage current, and you are going to, I mean, that is basically going to be noise. So you amplify that, even that will get amplified. Okay, and many times noise also from surrounding may come. Now, surrounding, when I say you are clicking a picture here sitting on Earth, and some surrounding noise is going to be the light scattered by the air molecules. So if and depending on wavelength, you know, the red wavelength and the blue wavelength, they will get scattered by different amount, and your sensor will collect that kind of light. And the dust particles are there, then dust particles will scatter a lot of light, and that will again be collected by your camera. So when you are going to amplify, it is also going to amplify the noise. So one has to play with that. Now you keep exposure for a long time, what will happen is you will get a star trail, because now this is how one can aesthetically create a picture. Again, picture by one of my students, Shubhankar Vadke. When we go for stargazing, this particular picture was clicked. He kept camera on for a long time, and actually not a thing, not just one time. He kept camera on for a long time, but then in different kind of shots, and all those shots were ultimately digitally added together. That's called stacking, and then you get something like this. So they were added digitally. Okay. Now, why large aperture becomes useful? In astronomy, all objects are at very large distance. So depth of image is not an issue. But there is another addition, another importance. Okay. That importance is because of the diffraction. Now let us see what is this. So a point object ideally should produce a point image. So this is the point image. In reality, what happens is it doesn't produce a point image. Practically, it produces the image like a disk. So it's called airy disk. And there are diffraction patterns. And the central disk is airy disk. And there are going to be this is the first order minimum, second order minimum. So this size is going to be the size of airy disk. And why this happens? Because that aperture is going to have, aperture means what? You're going to have a lens or a mirror, okay, and then that is going to end at some particular point. The mirror ends at some particular point, okay. So that is going to create a diffraction because it is going to end at some point. So light is going to bend over the edges. It is going to spread effectively, and the angular size of the central disk is given by 1.22 lambda by d, where lambda is wavelength, d is the aperture. Larger the aperture, this disk size will become smaller and smaller, and that's why going for larger aperture telescope is more useful. And that is what one can see. But this diffraction pattern we can see even in CDs. For example, there are pits and slots. The old CDs or DVDs, if you have seen, okay, they will have different pits, and the diffraction is wavelength dependent phenomenon, and therefore you will see when the light falls, okay, different wavelengths will get diffracted by different amount, and you'll see colors. Now, diffraction you can see even in the sunlight. Okay, you won't see colors, but you can see sunlight. The haziness at the edge, okay, is because of the diffuseness at the edge is because of the diffraction. Of course, this is the pinhole effect. But here I want to show you the edginess. This edge is diffused edge. It is because of the diffraction. So we say the images are well resolved, okay, when the two airy disks are separate. When they start overlapping, what happens is the images are merged. Now, who decides? The distance between the two objects may be fixed in astronomy, okay, or in reality also. If I can make the airy disk small, then the two disks will be separated. And in order to make airy disk small, I will have to use larger aperture. Okay, so if images are too close, point is two diffraction patterns, and our eyes will see them separate only if the airy disk is small. Okay, and that's what we see here. This is the picture of the same area by Spitzer Space Telescope, which was having aperture of 0.85 meter, infrared image it is, and James Webb Space Telescope, which is about 7 times larger, 6.5 meter aperture. And you see, look at the dot size. Okay, it is not only collecting more amount of light, but it is also making each image very sharp. And that's what the airy disk, when it becomes small, the images are really becoming sharper. So yeah, now how does one overcome the noise? So high amplification will cause noise. Noise is going to be unwanted signal, either due to surrounding or due to electronics. We saw that. Adding multiple images of the same object will add up the signal, and it will average out the noise, because noise is not going to be perfect. No noise. Sometimes at one point of time, the noise will be at high at one particular point. At another point, if I click the picture again, the noise is going to be low, and effectively it will average out. So this is a picture again taken by one of my students. Okay, this is the single click ring nebula picture, and you see that the ISO number was kept so high that there's a lot of noise over here. Now you add 50 pictures. So he stacked what is called stacking, 50 pictures, and you see the clarity of this ring nebula. You may do additional processing to remove noise using software these days. And you can see this is again another astronomical picture clicked by Mr. Philip Almeida, another student of mine, where you see here the Lagoon Nebula, but you can't easily make out that this is a blurred image and there's a lot of noise over here. But then you again take larger number of photographs, you put them together, add them digitally, and this is what you get. So stacking and processing will give you something like this. You can see the beautiful clusters over here, and the nebula over here, okay, and the nebula over here. And this is typically done with simple cameras and stacking techniques. Electromagnetic spectrum is wide. The visible light is a very small region. You can click pictures in ultraviolet, you can get pictures in X-rays, you can get pictures in gamma rays, okay, and in different regions. So imaging with invisible light, why do we even bother about invisible? Because a lot of information is contained in the electromagnetic waves beyond visible light limit. Development of electronic devices help us to collect such information, and comparison with visible light imagery of the same region can help us build better understanding. This is what typically done in astronomy. There people do multi-wavelength astronomy. So the same region can be studied in one X-ray, same region can be studied in infrared region, same region can be studied in ultraviolet, it can be studied with visible light, and then ultimately you develop a picture of what exactly must be happening there. Now, it's not only about astronomy. We can do that in medical field, imaging different organs. So you see there are different techniques used. X-rays are used, MRI is used, CT is used, PET scan is used. What are these? X-rays are blocked by heavy elements. Bone will block them mainly because of calcium. Okay, but not soft tissues, because calcium is a relatively heavy element. And the soft tissues are mainly made of water, carbon, hydrogen, oxygen, nitrogen. Okay, and these are relatively light element as compared to the calcium, which is atomic number 20. Okay, whereas we are talking about the soft tissues are made up of mainly carbon, hydrogen, oxygen, nitrogen, and so on. MRI make use of it doesn't use ionizing radiation. So MRI will make use of high magnetic field, and the protons in the body will start emitting radiation. So protons are there in body because protons are nothing but hydrogen nuclei. So hydrogen is there everywhere. When the water is there, hydrogen is there. Okay, and our body is 70% water, and of course even other muscles, carbohydrates are there, so oxygen is going to be there and hydrogen is going to be there. MRA mainly focuses on blood vessels, and you can clearly see over here that this is magnetic resonance angiography, okay, MRA, which focuses on the blood vessels. CT scan is again uses X-rays, but X-rays are typically two-dimensional pictures. The CT scan is going to talk about 3 dimensions because you're going to use X-rays along different directions. So different slices will be taken. You use computer to build a basically 3D model, which doctors will understand if they want to find out certain thing out of CT scan. Similarly, one can use PET scan, positron emission tomography, okay, which is again, positron emission will be happening because you are going to, you will be given some kind of medicine which will contain the radioactive isotope, and that radioactive isotope is going to emit, with its half-life, emit positron, and that positrons will be picked up, okay, by the sensors which are kept around, and again, it will have 360-degree imaging. So, which means because that emission can happen in any direction. So you will have 360 degrees of imaging, and effectively you will build a 3D model of particular organ. And this becomes again useful wherever that particular medicine will be absorbed. This is basically how the body is going to function. Accordingly, the imaging will take place. So X-rays and MRIs are basically 2D images, though MRI uses 3D principle. Effectively, final image is going to be 2D image, whereas CT scan, PET scan is going to be, you are going to scan it throughout, okay, and you are going to construct using computer, you're going to construct 3D image. You can replace electrons, okay, because we know de Broglie wavelength, the lambda is h by p, and smaller the wavelength, larger is the momentum. And we also know for imaging, smaller wavelength is better resolution because it was that area disk was lambda by d. So small wavelength I can use, I will get a smaller area disk, I will get better resolution. And this is one of the these kind of pictures were famous when initially these electron microscopes became popular. That this is the ant head, okay, and you can see the clarity of the picture. Okay, this is the basic schematic. So where the electron is going to be there will be anode to accelerate those electrons, to give momentum of those electrons. Then you want to focus the electrons using magnetic lenses and so on. Ultimately, it is going to get scattered by the specimen over here, and then those scattered electrons are going to be collected by the sensors, and then those sensors from at different points, from where the electrons are coming, is going to ultimately construct the image. The point here is the electrons are basically used as waves and high momentum electrons will have smaller wavelength, and you will have better resolution pictures. There's a new technique of AFM. It is like a Braille system. Okay, that I mean, somebody who is visually impaired, how does he see the world around himself? So he's going to touch, sense whether there are ups and downs, or he may use a stick, and the stick may tell him while walking whether there are ups and downs, and he's going to use the stick. Now that kind of stick is there in this atomic force microscopy, and that stick will effectively tell what kind of surface is it. And these are some of the photographs. Okay, and these numbers are the characterization of that particular the thin film that he was constructing. Okay, but these are the kind of images that people are nowadays used for their research. Last question, but very important for our topic: why do we even rely on pictures? When the study was done by Randall Smith, okay, where beautiful pictures from Hubble Space Telescope come, and they are given out to different places, and in different museums they are put, different kind of science museums they are put, or planetaria they are put. Okay, and people watch them, and so a survey was conducted. So it turned out from that study that images become more attractive if they're given more information about them. So people, once they know what the image is about, they find image itself better. And this is a perception, because you are not only looking at what picture is, but you are also told what it is. And once you are told what it is, okay, you start getting meaning out of it. The picture starts telling story, and all human beings basically are story lovers. So you tell a good story, okay, people are going to appreciate. And here the examples of the false coloring of the images. So like we talked about those red filter, green filter, and so on. Okay, how do I get an image in radio wave? How do I get an image in X-rays, or how do I get image in infrared? Okay, I don't see infrared. So what is done is typically you will decide that this, I mean, the different filter, the same particular area will be different in different filters. You will take the image. Image is going to be grayscale. Image is going to be black and white. It's going to be intensity and darkness. Okay, but then will decide manually that if the image is coming with this particular wavelength, I'm going to color it with this. If the image comes with another wavelength, I'm going to color it with this. James Webb Space Telescope is going to be infrared telescope. Okay, mainly infrared telescope. Small amount of red region is going to be there. Now I want to create image out of that. What typically will be done is the larger wavelength, generally they will stick to the same thing. The larger wavelength infrared will be painted with red, and smaller wavelength infrared will be painted with blue. Typically the same thing is said. Why? Because even for scientists, okay, the imagery tells us some better understanding, and therefore you can make the good connection. Now take for example here radio image. This is the Crab Nebula. The green shows the radio emission from the unbound electrons, okay, around the inside the nebula. So basically that star had exploded, and the hydrogen gas is moving around. The star was exploded. It was seen some 1054 AD. There are inscriptions and there are written records in China and at other places. So we know about that. And with even normal telescopes, we know the amateur telescope, it is possible to see Crab Nebula. Okay, it's one of the beautiful objects in the sky, but you can see the fuzziness of course you can't see this kind of clarity because these pictures are taken with space telescope or larger telescope. In the optical image, the blue region is due to accelerated electrons, and the red region is hydrogen emission lines. Okay, now why this information is given? Because this is false coloring. These are not the real colors. Okay, different filters are used, and with those different filters you are going to ultimately paint them to see kind of structures which are happening over there, which will help also to build good computerized models. What happens when supernova takes place? And there are going to be X-ray images. So again, in all these different wavelength regions, you are going to effectively have the beautiful meaning. Now, this is one picture of Horsehead Nebula, original frame where Wilhelmina Fleming from Harvard Observatory, she discovered this. Okay, now this particular region is a beautiful region. With amateur telescope, of course, you can't see this. Okay, you need a professional telescope to see that. But when Hubble Space Telescope click that in infrared region, okay, you can make out this beautiful thing. Now, why you are able to make out this beautiful thing? The things that will come to scientists, astronomers from Hubble Space Telescope is digital data. But when they construct that into the visual image, Okay, that is going to tell a story that is not only going to be beautiful, it will also talk about what kind of effect would be happening over there. Okay, so this gives something, a nice picture, a good imaginary for people to understand. This is data of focus again picture, and you see that whenever false colored pictures are there, it is useful to see which color represents what. In this case, the green is, you can see the filamentary nature of this green region. This is mainly the dust surrounding the star glow primary at short infrared wavelength. The red is the area of the shock, okay, that is happening, and there is a bright bow shock. Okay, in this world normally will be seen in visible light also, but generally it is hidden behind the curtain of dust, and therefore infrared image will basically nicely show this. So again, this was clicked by Spitzer. More about this image can be seen, and we come to the last part. Okay, that there is something called bullet cluster, and this is the visible light image. In the X-rays, if you see, you get something like this, which means some kind of violent phenomena must be there because huge amount of X-ray is given out. And when you compose all these images, what you realize that two galaxy clusters basically pass through each other. And that created a lot of violent phenomena. The two galaxy clusters have just crossed each other through this. And looking at the images behind, people realize that these images are shifted, and probably because of the gravitational shift. And that gravitational, the gravitational shift probably is because of the dark matter. And so here there is a composite image of the X-ray region and the contours where the dark matter could be. Okay, but this doesn't give great understanding. What is beautiful is this. So you can give a superimpose where the dark matter could be. So this is visible light plus dark matter, and when you put everything together, okay, this is the kind of image you get. Okay, which gives a better understanding of where the dark matter probably is lying, how the galaxies pass through each other, where are the violent phenomena happening. So thank you very much. These imagery and these techniques are now helping us to see invisible things, dark matter, and give us one of the best stories. We are in the times when we are unfolding the great stories about what is happening in the universe and world around us. Thank you.
Thank you, sir. It was such an insightful talk. You covered the science of imaging so in such a vast manner, covering almost every field. So, and such spectacular pictures you have used. It was very interesting, very enlightening. Thank you so much. I think all our students and teachers who are attending, they have enjoyed. Yeah, somebody is saying science uncovered. Very true.
There is a question, sir. Please throw some light. Life is photon or something else? Your lecture is very interesting.
Okay, thank you for the compliment. And
so, sir, the question is, life is life, not light. Okay. Is it light, Dr. Sanjay Kumar, or life? I think he wrote life. Dr.
Yes,
Sanjay Kumar?
Yes, ma'am. Life. It is life.
LIGHT, right? Or LISE?
No, sir. It is life.
Could you write on chat box, please? Whether you mean life or light?
Yes.
So, sir, you have several compliments regarding great session, amazing session. And I think, I'm congratulating myself that I decided that you must be a speaker in this very important series where simple images are then finally connected to the whole cosmos. And some of the students here, they have studied radiation safety and are aware of MRI images and X-rays and X-ray spectra and so on. And it is such an enriching thing to note that a simple thing, which is like an image to us, a simple photograph we are taking day in and day out, how it is linked to such very, very important things in the universe.
Thank you, ma'am.
Dr. Sanjay Kumar says
coming
life.
To his
life
question,
is
he's saying life, and the question is life photons or what? The answer could be philosophical, but let us stick to physics. So life is basically, we may say, the complex interplay of matter and energy. And in that complex interplay of matter and energy, because there is going to be a feedback system, because there are non-linear system, it's basically a chaos constructing into reduction of entropy. So life, as we understand today from physics perspective, is emerges due to chaos. I mean, I'm talking about the technical term chaos, and that can lead to generation of reduction of entropy at some particular scale. So I mean, that is the answer that I can give. So photons are energies, and the atoms are matter, and it is interplay between matter and energy. Okay, which software is used for stacking?
Yes.
Stacking here. There are different kind of softwares which my student had used. Let me quickly refer to which software talk about.
Sir, your voice is breaking a bit.
Yeah, just a minute. I'm just quickly referring to my student who used. He said he has used the Ioptron Sky Guider Pro and refractor telescope, and he used Sequator, stacked in Sequator, and he processed in Photoshop and Lightroom. Okay, so I'll type that here. Stacked in Sequator and processed in Photoshop and Lightroom. So these are the softwares he used.
So, sir, you have further compliments, no words to express our gratitude. And further, it's an amazing technological story which we could have never known if we were not part of this session.
Thank you.
I think,
Thank
sir,
you.
words are few to give you compliments and to congratulate you and to also be grateful. We are all grateful that you have given us a wide coverage. And I'm sure everybody here who has attended the session would like to have more sessions from you. And I'm sure we'll be able to arrange more sessions with you, because the knowledge that you have amassed over the years in such an important field is really amazing. So I would now request all the participants to switch on their videos for a moment if they can, so that we can take a screenshot of our memory. And at the same time, I would like to announce that there was a technical glitch in the morning, but this whole session has been recorded, and after the recording is saved, I shall upload the whole recorded video onto the same YouTube channel of Nasi Delhi chapter. Every day the YouTube channel remains the same. It is that of Nasi Delhi chapter, and the Zoom link also remains the same. So there should be no worries about that. Thank you very much. Dr. Rachna and other faculty members of Physics department are also requested to switch on their. So thank you so much. And we can have a quick screenshot of our presence here. Thank you so much for it. I really thank each and every one of you again and again, all the faculty members and all the students and all the persons who patiently waited. Today's lecture, the whole will be uploaded on the same YouTube channel for all those who have missed it today in the beginning part. So with those words, thank you so much once again, and we hope to meet each other again very soon with the third lecture that is tomorrow. And with those words, I thank Professor Mahesh Shetty again.
That is on Saturday.
Yes.
Next lecture is on Saturday.
Yes, Saturday morning. The next lecture is on Saturday morning, and we will be giving announcements on the webinars list WhatsApp group as usual. So with those words, I thank you once again, and I thank Professor Mahesh Shetty once again.
Thank you, Professor Shetty.
Pushpa ma'am and Punita ma'am, I would like to congratulate you both. You are really have been organizing very inquisitive workshops and sessions. It's a great learning experience, ma'am.